Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we're going to look at graphing of piecewise defined functions, and we're going to, of course, consider this in consideration with the first, of course, the set of discussion we have had on the definition of piecewise functions. And we stated that this is going to be a range of functions which are going to be defined by two or more equations of a specified domain. So in this case, I've given the function g of x being represented by three equations of x minus the square of x minus 1, x minus 1, and 3. And this specific set of equations have been given a set of domain which I've given in terms of x, which is a set of values between these specific open and closed intervals given as such. So if we try to look at this, then therefore in trying to do a graphing of this specific piecewise defined function, we're going to take a set of each equation and try to graph it in its individual aspect and try to see how we can be able to combine them together to form a general illustration for the graphing given in our last set. So we're going to start with the first one, and then I'm going to give these ones just specific values over the Cartesian coordinate system for, let me give this one as A, B, C, and D. So D is going to form our compounded set of these three equations that I'm going to put on that far side of the top right side of the board. So in this case, I'm going to start with the first one. So our first set is going to be a graph of the function gx equivalent to the square of x minus 1 over this range of values for negative infinity and 0. So therefore, it's going to range, values for x are going to range, we just give them as such. So this is y, x, x, y, x, y. So the range of values for x are going to range between closed boundary for this positive, the 0 value, and towards the negative, or rather towards the negative x-axis to negative infinity. So if the value for x squared minus 1, so if we do a substitution for a negative 1 in this specific case, we're going to see that the value for, or rather if the value for x is equivalent to 0, then if we do a substitution in this specific case for the function of x or the g of x, we're going to see that the value of x is going to be negative 1 at this specific point. And then if the value of x is equivalent to negative 1, then this value for, of course, this specific value, then we're going to find the value for g is going to be equivalent to 0. So for negative 1 value of x, the value for g is going to be equivalent to negative 1 given as such. And then we're going to see that we can be able to do a plot of this function. So this second coordinate, if x is equivalent to 1, then this value for y is going to be equivalent to 0. So it's going to lie along the x-axis. So we can be able to do a plot of this, and it's going to give us a graph that is going to assume this specific nature. So therefore, this is going to be a graph of x square of x minus 1 being illustrated as such. So for the second case, we are going to look at the graph of x minus 1. And in this case also I'm going to give these values for, so this is the origin at 0, negative 1, negative 2, 1, 2, 3. And this is of course negative 1, negative 2 given as such. And this is a positive 1, 2, 3, and 4. Of course, I can give a range of values for that. So this is going to be a graph of g of x is equivalent to x minus 1. And if we try to substitute it with some values, so in this case, if the x is equivalent to 0, then therefore y will be equivalent to negative 1. So we'll have a plot at that specific point. And if x is equivalent to 1, then therefore gx is equivalent to 0. And this is going to give us a plot of a graph that is going to, of course, pass through those points given as such. And this is going to be the graph of x minus 1 given as such. So the gx is going to be equivalent to x minus 1. This is going to give us the graph of that specific nature. So for that, the third set of range of values for x, which is a set of values for a closed interval for 4 and positive infinity. And then therefore we're going to do a substitution whereby the value of x is going to start from 1, 2, 3, 4. So at this specific point, you can be able to just do a demarcation for that. 1, 2, 3, 4, 5. So at this specific point, we're going to see that if at the graph, if x is equivalent to 4, then therefore gx is going to be equivalent to 4 given at this specific point. And then the next set of values are going to consist of positive infinity. So we can be able to illustrate that graph just by having that point, having an arrow pointing in that specific direction. And this is going to represent a set of values for this specific graph showing an arrow going in that specific direction. So a combination of these three specific graphs is going to give us a piecewise defined function, and of course which is going to consist of those specific graphs. So I'm going to have this one as -1, -2, 1, 2, 3, 4, and then we're going to have -1, -2, 1, 2, 3, 4. So for the last graph that we have had, it's going to be a straight that is going to point towards infinity. And for the first graph, we're going to have it having plotted points of -1 and 1 as such. And this was the graph of the square of x minus 1 gx given as such. And then we're going to have this graph passing through -1 and of course +1 of x given as such. So the combination of these three graphs, for the first one, which is here, the second one, which is a straight from a -1 to this specific point for 4, is going to combine with this third one for gx, for x is equals 4 to positive infinity going in that direction. So the combination of this specific graph is going to give us overall graph for g of x, which is going to be a piecewise defined function given as such. So basically, that's a strategy that we're going to use in defining or graphing or other piecewise defined functions. And in some cases, we're going to see that there are some points which are going to have a break, whereby the graphs are not going to be continuous. And that one we're going to look at it at another video. So for this, I wanted us to have a concept on how we can be able to graph a piecewise defined function. And as I've said, in a summary form, we're going to take these specific individual equations with their set of the domain given as such, and then try to do a plot. And then finally, we're going to combine the graphs for A, B, C in order to come up with an overall graph of g of x given in that last set for D. So this is it for now, guys. Kindly check in our description boxes for various links of videos in mathematics, basically in other application areas like physics, so that they can be able to complement on this specific discussion we have had. So that is it for now, guys. Bye, God bless you.